Okay, I think we'll get started. Welcome to the afternoon session. We have 4 talks. We'll start with invited talk by Stephen Jordan on quantum and stochastic optimization.
Thanks. So this is joint work with all these people here, but most of what I'll report on in this talk is with Adiabatic, who I think is in this room somewhere, and also Jake Bringawat, who's an undergrad researcher. So as many people have mentioned in other talks, the Hamiltonians that we usually use in our physical implementations and also in many of our algorithms are stochastic Hamiltonians, where all of the off-diagonal matrix elements are non-positive. And this implies that the ground state of these Hamiltonians can be expressed using all real positive amplitudes. And so these ground states look a lot like probability distributions. They're just normalized differently. And so it raises a question of, well, if you have all these positive amplitudes, there's not any obvious destructive interference going on. Could you actually simulate these processes using some classical probabilistic process? Or if you want to formulate it in a complexity theoretic way, you could call this the P versus stochastic P question. Is it true that classical algorithms can, in polynomial time, just simulate everything that stochastic adiabatic quantum computers can do or not? And I think that's one of the really interesting foundational questions in our field of adiabatic computing. And that's sort of, that question is kind of the motivation behind everything I'll talk about today. So another thing you can observe with stochastic Hamiltonians is that you put one into a Schrodinger equation, and except for this factor of I there, it looks a lot like a diffusion equation. So you can write down this analogous diffusion equation, and you could think of this as being a continuous time random walk, where these off-diagonal matrix elements are giving you probabilities for walkers to hop to other sites, flip bits in other words, and the on-diagonal elements are giving you some probabilities for the walkers to either die off or to reproduce. And so it's kind of like a diffusion equation, but it doesn't preserve the norm of this vector psi. In particular, if H is a positive semi-definite matrix, then this norm is going to shrink with time. So this is some kind of mathematical analogy. You are sort of rotating to imaginary time, and the question is, what can we learn from this relationship between these Schrodinger wave equations and these closely related diffusion equations? And so this talk really consists of 2 parts, each having to do with that theme about this relationship between these wave equations and diffusion equations. But other than that, the parts are fairly separate. So just to summarize what I'm about to tell you, the first part of my talk will address this question of whether these continuous time random walks described by this diffusion equation could be used as classical randomized algorithms for simulating stochastic adiabatic computing, and whether those algorithms would be efficient. And that's actually what I spoke about at AQC2017 1 year ago. And we found an example where stochastic adiabatic computing had an exponential advantage over the corresponding classical random walk. But our example was not a local Hamiltonian. It involved n-body interactions. And so the progress since then, in fact, I believe last year at AQC 2016, someone raised their hand at the end of the talk and said, but your Hamiltonian has n-body interactions. What about if you restrict your attention to, k local Hamiltonians for some fixed k? Is it then possible to have a diffusion algorithm that simulates all of stochastic adiabatic computing? And at the time, my answer was, well, I don't know, but I'll think about it. And so since then, in collaboration with Jake Bringawat, I have thought about it, and now we have a 6 local example with the same character. So even if you restrict your attention to local Hamiltonians only involving 6-body interactions, for example, it's still true that's powerful enough to do something that this direct diffusion Monte Carlo simulation will not be able to track efficiently. So the second part of my talk is really based on a really neat paper that came out about a year ago by Yang, Ramani, Shabani, Nevin, and Shimon, which presented a control theoretic framework for thinking about quantum optimization algorithms, and including both adiabatic optimization and these quantum approximate optimization algorithms. And I thought this was a very neat paper because it allows you to bring in a big, highly developed body of mathematical theory that was worked out over the many decades in the classical control theory community and apply it to the design of these quantum algorithms. And one thing you can notice right away about this is that the same theorems apply just as well to these analogous stochastic algorithms, these ones described by the diffusion equation as opposed to the wave equation. So Aniruddha and I have been looking at sort of exporting these ideas that Yang et al. Introduced into the design of quantum adiabatic algorithms to the design of analogous classical stochastic algorithms. And this is ongoing work, but we've already found one example where by applying these techniques, we can actually get an exponential improvement in the performance of a stochastic optimization algorithm, specifically simulated annealing, relative to what you get using kind of quasi-static, smoothly varying, unoptimized simulated annealing. So now I'll go through these two pieces of my talk, these two parts in order, starting with the first one about diffusion Monte Carlo. So a few slides ago, I wrote down this diffusion equation where you take the Hamiltonian from your quantum algorithm and you just take away this I in front and you call that some kind of continuous time random walk. Now, if you just do that naively, you won't get a good classical algorithm because the norm of this vector p, which we can think of as kind of a probability distribution for the distribution of random walkers, will have a norm that either exponentially blows up or exponentially decays to 0. And so to avoid that problem, what you can do is you can just add an adjustable identity term into your Hamiltonian, which you sort of control by a feedback loop. If your population is dropping too low, you decrease this, or I guess increase this coefficient to bring the population back up by having more walkers reproduce and fewer die. And if the population's getting too high, you do the opposite. And so this kind of diffusion equation plus this little feedback loop is basically diffusion Monte Carlo. And it's kind of a very natural way you could try to simulate stochastic adiabatic computing using classical computers. You could think of this as an obvious proof technique that you might attempt if you were trying to prove that stochastic p equals p. But for it to be a proof that these complexity classes are the same, it would have to always work. It would have to work on every instance. And that is not the case. And the basic intuition about why this can fail is that in the diffusion Monte Carlo algorithm, what you're doing is tracking a probability distribution which is not proportional to the quantum probability distribution of psi squared. It's just directly proportional to psi itself. And so you might think, oh, well, that couldn't make a very big difference. That couldn't make an exponential difference. It's just squaring something, so it's a quadratic difference between these things. But that's not quite right, because these probabilities need to add up to 1. And so the probability distribution that you get is psi divided by the sum of all the amplitudes. And this sum can be exponentially large. Think, for example, of the uniform superposition. The amplitudes are 1 over root n. You've got n of them, so this can be an exponentially large number. And so that means these probabilities on a given site can sometimes be exponentially smaller than the probabilities you would have on that corresponding site according to the probability distribution psi squared. So the idea of our counterexample from last year and also of our counterexample from this year is to exploit this discrepancy between these two probability distributions in order to find a problem on which adiabatic quantum computing exponentially beats stochastic random walks. And so that's the idea. We carefully tune some potential in our problem so that this probability distribution that the diffusion Monte Carlo tracks is exponentially small across some barrier, and so the walkers sort of can't colonize the other side. Basically, the way that walkers can tunnel is on some high energy place they start dying off, on some low energy place they start reproducing. That's how they can cross barriers without having to walk across them. But they can only do that if there's some walkers on the other side of the barrier already, and if that probability is too small, you need to have an exponentially large number of walkers for this kind of pseudo-classical tunneling to occur. And so you tune things so that doesn't occur, but quantum tunneling does. And so here's our example from last year. It was another one of these problems where the potential depends only on the Hamming weight of your string. These are a theorist's favorite examples because they're quite analyzable both analytically and numerically. And the details are not so important, but we had some example like this where quantum tunneling worked and classical tunneling of walkers didn't work. But you'll notice that this potential, it's very funny looking. It's got this minus the projector onto the all zeros state. So this does not correspond to any local Hamiltonian. This involves n qubit or n bit interactions. So after seeing that example, one could, if one was kind of a diehard believer in the idea that diffusion Monte Carlo ought to be able to, simulate stochastic adiabatic computing, such a person could have kind of a fallback hypothesis, which is that, all right, if you restrict your attention only to local Hamiltonians involving some k-body interactions for a fixed k that doesn't depend on n, maybe you can still simulate everything efficiently using these classical probabilistic algorithms. So you might say diffusion Monte Carlo produces a probability distribution epsilon close to the ground state of any k local adiabatic process in time scaling polynomially with the gap and with this precision parameter. But now we have a counterexample to that too. So here's what our counterexample looks like. So we have our usual hopping term minus the sum of the sigma x's. And then we have some potential which depends only on Hamming weight. So we can think of it as being some function of the sum of the sigma z's. And this function is a degree 6 polynomial. So that implies that this Hamiltonian only involves up to 6-body interactions. And in some sense, what our polynomial looks like, so this polynomial has coefficients which depend on s, this parameter that we vary from 0 to 1 during our adiabatic process, so that the potential shifts over time. And initially, we have a well which is centered at n over 2, the middle of the, the most likely Hamming weight. And then that potential rises, and this potential well lowers, and later on, the favored well is one which is above n over 2. And so initially, the ground state is to be over here, and at the end, the ground state is to be over here, and somehow you have to, in the quantum case, tunnel across, and in the classical case, the walkers have to sort of reproduce over here and die off over here to do this classical analog of tunneling. And so again, we analyze this, and by tuning the parameters just right, we could get it to be the case that the eigenvalue gap in the quantum case was polynomial, but the tunneling time for the classical case was exponential. So basically, where did this potential come from? I mean, the intuition is pretty much this, and everything else was pretty much trial and error. And the way we analyzed it was maybe more interesting. Basically, we used this method from this nice paper by Brady and Van Dam, which actually is kind of a formalization and elaboration of some ideas in an earlier Farhi, Goldstone, and Gutman paper, which which basically tells you how to analyze these kind of these potentials that depend only on Hamming weight. And then so this allows you to transform your problem into one which is just a conventional quantum mechanics problem in one dimension, like the sort that you do as an undergrad. And that also ended up being a double well, which we then analyze using a tight binding approximation and test against exact numerics. So just to give a flavor of how this works, again, here's our Hamiltonian. And it's not hard to see that this Hamiltonian is invariant under permuting all the any permutation of the qubits. So there's a lot of symmetry in this Hamiltonian, and in particular, there's a subspace which is the symmetric subspace. In other words, for any given Hamming weight, you have the corresponding uniform superposition over all bit strings of that Hamming weight, and there's n plus 1 such states for Hamming weight 0, 1, 2, up to n, and these states form an orthonormal basis for some subspace, and you start in that subspace and you stay in that subspace the whole time. It's one block of your Hamiltonian that doesn't couple to anything else. So everything you have to analyze about this Hamiltonian, its spectrum, its dynamics, everything else, is all happening in this n plus 1 dimensional subspace of the full 2 to the n dimensional Hilbert space. And that's what's so handy about these Hamming symmetric Hamiltonians. So you can describe your ground state at any given moment as a superposition over these basis states for different Hamming weights. And so now it's looking like a one-dimensional problem. You have some amplitude which is depending on a number, not on a bit string. It's just depending on this number that goes from 0 to n. And this Wien transformation business is about taking this one-dimensional problem and sort of in the large n limit, approximating it by a one-dimensional problem on a line segment on the continuum. So just think of these numbers 0 to n minus 1 as getting denser and denser on the unit interval, for example. And it turns out that the Hamiltonian, the effective Hamiltonian on that line segment, looks just like an ordinary undergrad kinetic term plus whatever potential you had as a function of Hamming weight plus some corrections. And in fact, this correction is pretty intuitive. You don't really need to go through all this fancy machinery. You could actually guess it. Because if you think about if this potential is 0, the ground state's the uniform superposition over bit strings. Correspondingly, the amplitude psi of x on h of x has to cancel out this square root of a binomial factor. So the ground state psi of x is looking like the square root of a binomial, which is like a Gaussian. What's a Gaussian a ground state of? We all know it's a ground state of a quadratic. So this is exactly the quadratic term. You can guess what the right coefficient is and everything just from that simple reasoning. There's also higher order corrections, and for that, you need to actually go through the machinery of this Wien transform. So anyway, we basically started with a double well potential on the line segment that had the properties we wanted in terms of tunneling and lack of classical tunneling, so to speak. And then we just subtracted these correction terms up to 6th order from that in order to get things to converge properly in the limit of n going to infinity. And so we tested this against exact numerics, and it looked so all that was exact, but the non-exact part is that to analyze the double well, we used the tight binding approximation. So we tested this against exact numerics, and it was very accurate. So we have 1 over the gap squared is scaling like n cubed, and the classical tunneling time is scaling like e to the n to the 3/4. So that's our counterexample, and it sort of refutes the stochastic diffusion Monte Carlo diehards who we can imagine might exist, who would say that, well, maybe if you restrict your attention to local Hamiltonians, you can actually simulate everything. Okay, so that concludes part 1 of my talk. And so now let me move on to the other half, which is about applying control theory, and together with exploiting this analogy between the Schrodinger wave equation and the corresponding diffusion equation that exists in the case of stochastic Hamiltonians. So as I've mentioned, optimal control theory is an old area of mathematics, very well studied, with a lot of surprising and interesting and non-trivial theorems in it that you can find in nicely distilled textbooks and so on. And so I thought it was a very exciting thing when these authors showed that this body of work could be applied to the design of quantum optimization algorithms. And specifically, their main point was that there's a theorem from control theory that is sort of a corollary of Pontryagin's principle, which says that if you have some kind of system like this, where there's a differential equation, the time derivative of the thing you're trying to control is determined by something which varies linearly with your control parameters, or even just monotonically, I think, then it will be the case, except in certain pathological circumstances, that the optimal control to drive your system into the state you want will be so-called bang-bang control. And what that means is, suppose this control parameter is restricted in its magnitude. This is a realistic assumption. On your physical hardware, you can't tune the couplings and field strengths as high as you want. So you say, okay, maybe just this parameter g can vary between, say, 0 and 1. And at any given moment, what you should be doing is have that g turned all the way up to 1 or all the way down to 0. The optimal thing is not to vary it smoothly. And this was kind of an argument which was suggesting the merits of the QA-OA algorithm, where you indeed switch this back and forth between 0 and 1, relative to the adiabatic optimization algorithm, where you just linearly vary this. Now, of course, this optimality theorem is just an existence statement. It doesn't mean that, you should just flip things up and down. It's only optimal if you know what the optimal moments to flip it up and down are, which you might not. But nevertheless, it seemed very interesting. And so there's actually kind of a different way of thinking about this, an equivalent way, which I think is maybe even a little more intuitive and gives you an idea of where this principle comes from. And so what you can think about is you can think about designing your optimal control trajectory as kind of a dynamic programming problem. So here's some, made up schematic parameter space, some target space, like in the case of a quantum algorithm, this would be the Hilbert space, and you have some objective function that you're trying to optimize at the end of your dynamics. So for the final state, say you're doing some process of time t, you know what the the payoff function of any given state in the Hilbert space is. That's just told to you. It's part of the problem specification. So now you can go backwards in time from there. You can say, okay, let's go a little bit of time delta t before that. What is the payoff that we're going to get if at this time t minus delta t we're in some particular location in this space and we subsequently do everything optimally? Well, you can calculate that point by point. So you can take a point in here and you can say, all right, if I turn my control parameter up all the way, that means this point gets mapped to that point. If I turn my control parameter down as far as it can go, that means this point gets mapped onto that point, and so on in between. And so amongst this little region that could be mapped to that point, depending on your choice of parameters, you pick the point that gives you the best payoff, and you say, okay, that's the value of this point at this time, t minus delta t. And if this payoff function is something that's varying smoothly, and if this little region that you map onto, according to your choice of parameters, is something like a little line segment, for example, then it's pretty clear that if in the limit that this line segment becomes very small, the optimal choice is going to be at one of the boundaries of that line segment. And that's basically where this bang-bang principle comes from. If your control manifold is something different, like instead of a line segment, it's a torus or something, then it's not going to be true that, I mean, there are no boundaries, so it can't be true. But that's not the case here. So then you could repeat this and calculate the payoffs at the previous time step and the previous time step and the previous time step and just sort of map backwards in time until at time 0 you filled in what's the payoff that I am going to get if I start at the following point and do everything optimally subsequently. And of course, as you're going through this backwards, if you remember what you're doing and keep track, you're also learning what that optimal set of parameter choices will be. So now imagine you take these little time steps to be infinitesimally small. This kind of dynamic programming prescription turns into a differential equation, which is called the Hamilton-Jacobi-Bellman equation, or I guess people sometimes just call it the Bellman equation for short, and this is what it looks like. So, as I said, if the control manifold has boundaries and the objective function is differentiable, then at each particular time, the optimal control should be on the boundary. As you can just kind of see by looking at pictures like this, it really does make sense. So there is, however, something pathological that can happen, which is called Fuller's phenomenon. And what that is that although the control is bang bang in some sense, what you can find when solving this equation is that the control hops infinitely many times between these two boundaries on your trajectory going across. So this is an example where the formalism can break down. Now, the reason I mention this, it's sort of a preliminary result at this point, but with Aniruddha, we've been looking at kind of trying to derive Grover's algorithm directly from this formalism in a systematic manner, and it preliminarily looks like actually the symmetries of the problem are such that this actually occurs, but that's still kind of to be confirmed. Anyway, something where we can have that we have analyzed more thoroughly is a rather neat problem from a paper in 2002 by Farhi, Goldstone, and Gutman called the bush of implications. And the point of this example was that it was a problem where adiabatic quantum computing solves it in polynomial time, but simulated annealing requires exponential time to solve it. And so the way the problem is you have a very small tree, or a bush you could say, and at the root is a particular variable, a bit, that we could call bit 0. And then on the leaves, we have n other bits, 1 through n. And our objective function is this. And what it means is that we can think of each of these branches as being a implies B clause in a constraint satisfaction problem. And so if this bit 0 is a 1, and this bit corresponding on the leaf is a 0, then you get an energy penalty of 1. But on the other hand, you also have a bias on this root bit, which tells you that it's lower energy to be 1 than to be 0. So you can actually kind of see why this is a hard problem, because at a given moment, if you do gradient descent, so suppose you start and like half these bits on average are going to be 1s and half of them are going to be 0s, then there's a huge energy advantage to flipping this bit from 1 to 0. That'll take away n penalties and only add 1 penalty for flipping this bottom bit. So that's a very likely thing to do for an optimization algorithm, but on the other hand, the optimal solution is to have this bit be a 1, which satisfies that, and all of these bits to also be ones, which satisfy the implications. So it's kind of steering a lot of optimization algorithms in the wrong way. So we looked at the bang-bang version of simulated annealing, applying this kind of Pontryagin principle to the simulated annealing problem on this simulated annealing algorithm on this problem. And so what would, in general, bang-bang simulated annealing be? In general, what it would be is that each time you either do standard simulated annealing updates at 0 temperature or at infinite temperature. So at 0 temperature, what the Metropolis update rule would be to sample one of your allowed moves at random. So in most examples we look at, the allowed moves would be flipping any of the individual bits, and then accept that move if and only if the energy is lowered. And it doesn't matter how much it's lowered, it's just accept if it's lowered, reject if it's raised. And infinite temperature Metropolis update is you just flip a bit at random. You do randomly one of your allowed moves, you don't pay any attention to the energy at all. So it's essentially alternating. So you have some bang-bang control trajectory, temperature infinite, 0, infinite, 0, infinite, 0, and you're alternating between something that's kind of akin to pure gradient descent and something that is exactly pure random diffusion. Although it's not quite gradient descent because you aren't going downwards in the direction of steepest descent, you're just picking any descending direction at random. And so if you apply this to the bush of implications, you can calculate that actually this works fine for solving that problem, unlike quasi-static simulated annealing. And the argument is pretty simple. So our particular trajectory is you start with infinite temperature and immediately switch to 0 temperature. So there's just one bang in this bang-bang protocol. And so now let's think about what happens when we do that. So since we started with the bits all random, there's a half probability that we started with this bit at the root equaling 1, which is what we want. It's equal to 1 in the optimal solution, although at early stages, gradient descent is going to encourage you to flip it to 0, which is kind of the wrong thing to do. And even in this algorithm, that could be a problem. But it turns out that this doesn't happen with overwhelming likelihood. So you can see that the initial state, let's call m the number of ones on the leaves. So initially that's going to be around n over 2 on average. And so if we were lucky, we got z, this root bit, to be what it should be, a 1, then the first accepted move will be we're going to flip any of the things where flipping them decreases the energy. M of those things are these leaf variables, where by flipping it we'd be doing the right thing, and one of them is flipping the root variable, which is moving us in the wrong direction. So with pretty high probability we're moving in a good direction. We'll flip a leaf rather than the root just because there's more of them. So probability m over m plus 1 versus 1 over m plus 1. And then on subsequent moves, it's just the same thing. Now m is 1 less. So the probability that we never flip this root bit in the entire process is m over m plus 1 times m minus 1 over m times m minus 2 over m minus 1, and so on. And you see just cancel, 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 cancel. This is 1 over m plus 1, which is 2 over n. And so we had a half probability of starting out with the root bit as what we wanted, and a probability of about 2 over n of keeping it there and never touching it the whole time. So we have a 1 over n chance of succeeding this way. And so how long does it take to carry out this process? Well, we have order n bits that we have to flip. So it's kind of like n steps, except there's also these rejected moves. Flipping one bit actually happens after you make a few rejected moves first, and that adds an extra log factor to the complexity. And so we need to repeat this process order n times to get it to work. So the total complexity of this is order n squared log n, a polynomial scaling. This n is the number of bits. So that is an exponential improvement over quasi-static standard simulated annealing on this particular example problem, which had previously been proposed as an example of exponential separation between adiabatic computing and simulated annealing. So that we thought was kind of an interesting example. And the big question we have is that an isolated example or is that the tip of an iceberg? And that's something we're still trying to figure out. But basically, we found that this relationship between the Schrodinger wave equation and this corresponding diffusion equation is quite useful. It does not directly yield an efficient classical algorithm for simulating all of stochastic adiabatic quantum computing, even if we do restrict our attention to k local Hamiltonians for fixed k. But it does allow us to export some ideas that this community is coming up with for the design of quantum optimization algorithms and export those ideas to improving classical algorithms too. So we kind of get a double payoff from every advancement that is thought up here. One thing that I think is very interesting in that respect is this idea that was talked about a lot at this meeting of advancing and retarding the annealing schedules for individual bits to make them all freeze out in a more synchronized way and improve the performance. I think that is another thing that would be very interesting to explore in the context of stochastic algorithms. So I think there's a lot of interesting things to do like that, and I hope that maybe some of you will join this quest, and thank you for your attention.
So if the difference between solving the Schrodinger equation versus diffusion is psi versus psi squared, how about you just plug psi squared into the diffusion equation?
Well, so a way you can get a diffusive process that gives you psi squared is using path integral Monte Carlo with closed boundary conditions. So then sort of like by tying the two ends together of this path integral, you're sort of squaring the wave function. And that does solve this problem. Like I'm pretty sure that if you tried path integral Monte Carlo on these problems, it should work fine. On the other hand, path integral Monte Carlo is subject to a different set of problems, such as the topological obstructions that Hastings pointed out. So I think it's actually possible to construct some very special and complicated example that simultaneously thwarts both diffusion and path integral Monte Carlo. Yeah, so maybe that would be an interesting thing to do in future work. I don't think it's the case that between the two of these algorithms they cover everything.
The next AQC.
Yeah.
May I? Oh, okay. My question is regarding to the Bambang control. If I remember correctly, in the optimization control theory, the Bambang control is more related to the optimize the control time or convergence time, and the objective function is to actually there's some target object function, and to reach the control value to reach the target value, and the objective is to minimize the time to reach the convergence time, rather than to optimize some cost function. And how do you how this can be related to the optimization of the cost function? That is my question.
Yeah, so actually you raise an interesting point, which is that there's a nice, very general formulation of this bang-bang control theorem, which I could write on the board, I guess, if I can drag it out. Well, maybe I can't. But basically, you can write down an objective function which is a sum of two pieces. One is a time integral of some metric of how hard you're working along the path, along the trajectory that you execute. And the other one is some boundary term that's just defined by the final state that you reach. And two special cases of that are you might have 0 as your integrand, And then that's the case where you have a fixed duration for your process, but you're trying to steer as closely as possible to some target state. Another limiting case is the boundary term is 0 and your integrand is 1. So now this first integral part is just measuring how long it took you to get to your target. And you can apply this Pontryagin formalism to the general case that includes each of these special cases.
Okay, so last question perhaps?
Yeah, so if I understood well in the first part of your talk, you cast your problem into a one-dimensional problem with continuous variable, and then you solve with diffusion Monte Carlo. And generally, when you don't use importance sampling, then your Markov chain is given by Wiener process. But I imagine that hadn't been you had used a trial wave function that could have been Gaussian-like, for example, because you know that your ground state has a form of a Gaussian. Then you have a drift Langevin equation, and then maybe since your probability distribution is changing from the ground state to the ground state time, the trial wave function, that could solve the problem, yes.
Yeah, I haven't worked it through in any detail, but I wouldn't be surprised if there exists some cleverly chosen trial wave function that allows diffusion Monte Carlo to work on this example. The reason, on the other hand, my feeling about these trial wave functions is that it's sort of a very cleverness-dependent kind of algorithm. I'm not sure how to formulate it as being something where the computer does the whole job in a completely general way and doesn't require human ingenuity to come up with specific trial wave functions in different cases. But maybe something like that could work. It's definitely interesting to think about.
Okay, let's thank Stephen again.